Okay, good morning. Welcome back. Any questions or comments? Okay, let me start. I want to start talking about Anderson localization today. So first, let me remind you, so what we had about, so we will talk about transport, and we'll see that to lowest order, what we have seen at this Boltzmann formalism is like transport is almost classical. What Rudd did like 100 or 150 years ago is almost 100% correct, right? But there are small corrections, and these small corrections are due to quantum mechanics. And we'll see these are because electrons are waves, and waves interfere, and this interference gives rise to localization, and localization is going to be a correction in conductivity or resistivity. So that's the goal, and I want to start with Einstein relation to motivate. And what we found here was like conductivity was equal to E squared dN d mu times d. So this dN d mu is density of states at Fermi level mu, and this one is diffusion constant. And so what may happen is, like typically we have like insulators. What this means is like conductivity is zero if density of states is zero. If there is nothing to carry charge, current, right? You cannot have current. If you don't have current, that means conductivity is zero. So that's the trivial case. That's what we call band insulator. And there are some other cases, but the interesting case will be even if you have like a finite density of states, even if the n, the mu is non-zero, we can have an insulator, or sigma is equal to zero. And for this to happen, right, there is only one way, right? E is like a fundamental constant. This is density of states, and we are saying that this is non-zero, and there is only one possibility is B has to be zero. And typically what we say to this case is like absence of diffusion. So now we have to have like a picture where diffusion terminates due to quantum interference. So the setup is like, okay, first we have like periodic potential, right? All solid state systems are coming to us with almost all solid state systems are coming to us with crystals, and the crystals have like some periodic potential. And periodic potential means we have like Bloch waves, and Bloch waves do not scatter. They don't have any localization. They don't have any resistance. Bloch waves just propagate in the lattice as if there is nothing. And on top of this periodic potential, we put impurities over periodic potential. And these are like, they can be like a variety of things. Maybe there's like a strange atom in the crystal lattice. There's like maybe like a substitution. Maybe there's like a dislocation. Who knows? But we don't care. And what happens is like Bloch waves scatter of impurities. And that's the mechanism of resistance. And this causes resistance. Otherwise, there is no resistance in a metal. So in this, so you can see we don't consider some complicated ingredients, they are always there, right? There's like, for example, there are phonons, they are always there. There are like electron-electron interactions, they are always there. But we have to simplify the problem. For the moment, we have only non-interacting waves and impurities, and even we are going to see even that one is going to be complicated. Then the question is how to get this D is equal to 0. And a short answer is going to be interference. And interference is a wave phenomena which is absent in Drude. Right? Drude formula thinks electron is like a classical ball. So before I think there's like some classic simplified argument. As I know, I think this is due to Anderson himself, and it is something like this. We have like a periodic potential, and the periodic potential, there is nothing, right? The electron just propagates on this like empty landscape. We are going to put some like disordered potential, maybe something like this. One potential here, maybe another potential like here, maybe another one is a little bit more shallow, maybe one here very deep, and another one here, something like that, and it just goes on. And okay, of course, lattice scale in this here is like much smaller, so it is like many lattice size, and there's like one disorder, many lattice size, and another disordered potential. And each disordered potential, we are thinking about like a quantum well. Maybe there's like some bound state here, maybe another one here, another one here, another one here, and another one here. So this is the available state. And you can see, like, we can think about like so energy like this, and there's, because of all these states, there is like a finite density of states, maybe some broadening, and they are like, so this is like distribution of energies. For example, there's like a one level here, there's like a point here, another level here, there's another point here, another level here, another point here. So the point of this is like, okay, this is density of states. Hopefully you are familiar with this kind of graphs. The density of states is finite, and I can think about a Fermi level, I don't know, somewhere inside the density of states. And the question is, how can, like, there is always like an available state above and below the Fermi level, right? And how can I have localization? How can I say that even though they like in the like metallic behavior, what we said was like, here's the Bloch energy band, here's the Fermi level, and if I have like an energy, there's always an available state to just go a little bit up, and that's the conduction. And here it seems like a little bit complicated spectrum, but still it seems like the same picture should apply. And the Anderson's argument, so any suggestions? Why would, okay, suppose this is my Fermi level and I have available states all over the place. Why would I have localization? What prevents me from like hopping in this landscape?
Maybe it's 0 Kelvin.
Like for the moment, yes, we are considering 0 Kelvin, but suppose there is like very low temperature. It's almost 0 Kelvin, but like there's always like, if I am here, there seems to be always a state in the vicinity of this energy graph. Why would I not just go there and then delocalize and contribute to conduction? So, and the answer was given by Anderson. So if you are like looking at the states nearby, like states nearby have different energy. And for example, if you look at this one, can you hop to this guy? At least at like 0 temperature, right? you cannot, right? This energy is here, this energy here. You need like some mechanism to like get this energy. Or if you are here, there's another level here, you cannot hop here. It's like zero temperature, right? There's no phonons, there's no temperature. So if you don't have energy, you cannot hop. So states nearby have different energy, so there will be no hopping. Exactly. So this is tunneling. This picture is about tunneling, right? So you go from here to here, and if you cannot, like, if you don't have anything to give you the temperature, right? Like there's like Boltzmann factor, right? Boltzmann factor, or like Fermi function, E minus E Fermi plus 1, which is approximately Boltzmann factor, e to the minus beta E minus E Fermi. But if beta is infinity, 0, nothing will help you. Right? At zero temperature, nothing can take you from here to there. And at finite temperature, you are going to have insulating resistance or insulating conductivity. That's another thing. For the moment, we are looking at this simple picture. Yes?
When there are impurities, we have zero modes, right? So I'm thinking it like if you are at the zero mode, then the density of states is also zero there. So I mean, maybe we have some infinite potential values at the impurities.
I mean, like this is the model, right? This is, for example, this one is like a impurity model. I have like perfect crystal lattice, and I model my impurity with like a shallow well. This one is a little bit another impurity, a little bit deeper well. This one is another impurity, and the problem is these impurities are going to have these like local states, and electron is going to go and sit there. So the first sentence is like states nearby have different energy, so they cannot hop because their energy does not match. But it seems like there are some energies that match. States with equal energy. So for example, here and here, right, in the vicinity there are two states. What prevents me from hopping from here to there? If you, of course, you cannot see in that picture, but just to have you like a...
Even a phonon transition.
There's no phonon here, right? There's just like right. So it's in this picture. So if the energies are equal, for example, this one and maybe this one, they almost have the same energy, but the wave function overlap is zero, right? This wave function is like very far away from this wave function. States with equal energy are what did I say here? Far apart, and that means no overlap. That means no conduction. That's the argument Anderson wave. So I want to comment a little bit about why this problem is difficult. So this is difficult problem because, like, if we had one impurity, so is this like a problem? If we had one impurity in quantum mechanics, what do we do? Right? Suppose somebody gave you like a single impurity, like a central potential in quantum mechanics. You just solve the scattering problem, right? Then solve scattering problem, and you are done. But if we had many impurities, but periodically arranged, what do we do? If we have like many impurities that they are periodically, that's the subject of this course. No, it is like not interference yet. Like I give you many impurities, but they are not random. I'm saying that they are like periodically arranged, like this. Yes, that's the Bloch problem, right? That's exactly what we like in condensed matter. So this is Bloch formalism. So we can also do that. But the problem in case is like many impurities, and they are like random or like disordered. Then we don't know what to do, right? There is nothing to do, basically. I mean, there are many things to do that we are going to go, but to begin with, it seems like a hopeless problem. And what we need to take is like, even if we have small disorder, even if the disorder like tiny, the crystal is gigantic medium, right? It goes, at least for theorists, crystal goes from minus infinity to plus infinity, and if you are in the infinite landscape, even a small thing comes to you many, many times, right? Even if you have like, I don't know, a 0.1% disorder, in the infinite landscape, you have to keep going on, and if you keep going on, you are going to bump into impurities over and over and over again. So there is like a repeated scattering from impurities, and that means like to disorder potential, we have to do perturbation theory to infinite order, because we have to scatter infinitely many times, and for that we have to like interfere. We have to get the interference from non-perturbative potential. Good. Now I want to introduce Anderson model. So Anderson model is kind of like a tight binding model, and it just strips out all the complications of like a real solid and shows us only two things, like a periodic potential and a disordered potential. Let me just write the model and let's comment. So previously we had this tight binding model. There was like some hopping, and we said hopefully you are now not scared of this notation. We are like hopping between nearest neighbors, AI, Decker, AJ, and most solids are described by this, right? If you have like a one-dimensional solid, this is like going to be cosine band. If you have 2D and so on, if you have graphene, you can just start from here and build the band structure. And Anderson considered on top of this, adding this on-site potentials, AI, Decker, AI. You can see this is like only speaking to a given site, and some over all sites. And AI were like random variables that were like given from like some distribution. You can take it from any distribution, but like let's take it from uniform distribution that is going to work for us, from W to W2, random variable. So that's the Anderson model. And I want to spend some time playing with this model and show it actually tells us about localization. So let's consider the limits. Let's consider the limit t much greater than w, right? If t is much greater than w, I can kill this term. And let's also, to get like a simpler picture, consider one-dimensional case. In the 1D, the Hamiltonian, I think we played with this Hamiltonian a lot. So this is like 0, 0, 0, 0. It's like 1, 1, 1, 1, 1, 1, dot, 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 right? Something like that. So this is the Hamiltonian. And we know how to solve this. For example, you can take the Fourier transform, and the eigenstates are going to be Bloch wave solutions. So that means this is delocalized. Right? So that's sometimes we are going to use the term delocalized. Sometimes we are going to say extended states. So this is the simple limit. The other, we can also consider the other limit. Suppose the disorder is so strong, we can kill this term, right? There is no hopping. Then So W is much bigger than T. Then Hamiltonian is just on-side potentials, right? This is approximately something like E1, E2, E3, dot, however many lattice sites you have, right? And what are the eigenfunctions of this Hamiltonian? Exactly, right? It's simple. That you can't get simple problem than that. So, for example, you have E1, and psi1 is going to be 1, 0, 0, 0. Another eigenvalue is E2, and psi2 is 0, 1, 0, 0, 0, dot, and so on. And if you look at this like a crystal, I have these sites. Maybe something like these are my sites, and dot, it goes on. So first eigenfunction is going to be something like this. Maybe I can also consider like turning on the small hopping, right? If there is no hopping, the eigenstate would be like exactly that, like this. But if I turn on like infinitesimal hopping, maybe it is going to be broadened here somewhat. Maybe another one here, another one here, another one here. And this thing is what we call it. Huh? Yeah, this is 100% localized. If you put just a little bit hopping, it is tight binding model and delocalized, but for this limit at least, this Hamiltonian is localized. Then the model, okay, we still didn't calculate anything from the model, but it seems like at least it is like reasonable to anticipate a transition from small t localized to small w extended states. So as we maybe you can think about fixing t, take t1 and tune the disorder. As disorder goes from small to large, we are going to go from extended states to localized states, and there will be like a transition. And this transition is what we call Anderson transition. Anderson, maybe localization. But it turns out, okay, so Anderson came up with this paper, I think in the 60s, and his paper was like very like simple arguments, very compelling, but this turned out to be like actually a very complicated problem. Just to give you a little bit spoiler, we will see transition exists only in 3D. And 1D and 2D are localized even for small disorder. Good. So what the picture will be is something like this. So if your disorder W is less than some critical disorder level, so here's the density states. You have some energy and some broadening, I don't know, something like that. So this is N of E. And if the disorder is smaller than critical, many states are delocalized, but still there will be these tails, right? These tails are going to have either like very small or very large energies, and what they will do for us is like, so these are going to be localized. So the center of the band is going to be delocalized.
What about the relationship between T
So I think I think that's a good point. Let me write it like this. Whenever W over T is smaller than some W over T critical, right? There is only one parameter here. I kind of took T is equal to 1. So the other limit, okay, so some states are localized, some states are delocalized, bigger. So this blue region is localized, and you can see there's like a special energy where you go from localized to delocalized, and this is called mobility H. Sometimes we show it with EM. And then the picture is, so if your Fermi level is here, you are in the localized states, you are like localized. And if you tune your Fermi level above the mobility H, you are going to be delocalized. And so this is like metallic behavior. You just keep tuning and tuning and tuning. As soon as you enter the other mobility H, you delocalize again. So that's the picture. If you have like a small disorder. But if your disorder is so strong, W over T is bigger than this W over T critical, all states localized. And this is the Anderson transition. And okay, at the moment you don't know this, but just I think it's good to keep in mind only in 3D. 2D is complicated, 1D is complicated, we are going to talk about that. But for the moment we can forget that detail. The next question is like, how do we quantify? Any questions? So how do we quantify localization? So what is the prop? Of course, it would be ideal to just look at the conductivity, but conductivity calculations are complicated. We want a simpler prop, and for that I want to introduce, at least from Gervin and Young, I want to introduce something called inverse participation ratio. So it is something like this, IPR. It is like some Q parameter dependent, and it is defined as, so this is the definition, and at any given dimension D, okay, let me write it maybe dr, it can be 1D, 2D or 3D, and this is psi of r. If you had like square, this is the normalization, right? And the participation ratio says you don't have Q, but you have psi to the 2Q. So if you have Q is equal to 1, IPR is equal to what? 1, because this is normalized, or it is constant if you forget to normalize. And if Q is bigger than 1, let's use dimensional analysis. And what I want to do is like, let me first start with localized states. For the localized states, IPR of Q is going to be, so from the volume I am going to get, right, so this entire state is going to be non-zero in some region of Xi, and from the Xi I have this is by the way localization length, I have from the volume Xi to the D. From the normalization I know psi should be 1 over L to the D, right? Because if it is normalized to 1, psi should be 1 over L to the D, right? Everybody knows this? Should I? Because we have D to the D, R, psi squared is equal to 1, the dimension of psi squared is 1 over L to the D, and L is the length of the system. Then psi to the 2q is going to have 1 over psi to the D q, right? Because from here, is that clear? It's just putting the dimensions. And this gives me psi to minus D q minus 1. I think I can erase this. And for extended states, IPR of Q, I just need to change psi to L, and it is going to be L to the minus D Q minus 1, because a delocalized state is going to be extended to entire system. So what we see is like this inverse participation ratio is this like finite for localized states, some number bigger than 0, and if you are in the extended states, take L goes to infinity, right? If L goes to infinity, and we are of course thinking about Q bigger than 1, in this case 0 for extended states. Okay. At least for a numerical study of a model like this. So this quantity, okay, of course we can come up with other quantities, but for the moment this quantity seems like a reasonable thing to study.
Why didn't we change psi to L when we get extended state?
So in the case of extended state, so we are trying to calculate this d to the d r psi to the 2q, and in this extended states, if you have like a system of size L in each direction, wave function fills the entire space. And I am saying like I don't care what psi is, right? I'm just trying to calculate the dimensions. So the dimension of this thing is integral contributes from every L point, right? Then I will have to put 1 over L to the D for the integral measure. But the dimension of psi is also like this. This is like 1 over L to the D is psi squared dimension, actually minus D, and I need to put Q on that. Is that clear? I don't take the integrals. So this is like, don't be scared. I just put the dimensions, and if I am localized, I just put psi, because localized state only thinks about small region. Delocalized states is speaking to entire sample.
L is very large, that's why you take
Yes,
0.
yes, exactly. So L is in the thermodynamic limit, L is large, and of course we are taking Q bigger than 1, 2, then this IPR is going to be 0. I mean, this is like a made up quantity, but right, this is in physics, we have to make up things. Especially if you are working in a hopeless problem, you have to make up things.
We just interchange L and psi, right?
Yes.
But the formulas not enough, I guess.
I think it is the same, right? So wherever I see L, I put psi.
Yeah, but you have there an L to D and L to DQ, but below the final line.
So this line?
Yes.
Oh, I think this one is incorrect. So sorry. So this one, the volume is going to be like L to the D, and psi square is going to be 1 over L to the D, but I don't have psi square. I have psi to the 2q, and this is I think going to do. Yes, I messed up a little bit. Thank you. Let me also talk about conductivity and then finish it there. At least take a break. Let's consider like Q can be anything you want, but typically I will, at least in the second hour when I study, I will just take Q is equal to 2, and that will show us a lot of localization stuff. So now I want to consider conductivity, sigma, with respect to disorder less than critical disorder or disorder bigger than critical disorder. I can also think about like if I can, as you have seen, I can, so there are two ways to think about this. I can either think about tuning the disorder, but in real materials we don't tune the disorder, right? In real materials we tune the chemical potential by gating, right? You apply gates and you give more electrons, and those more electrons are going to tune the chemical potential, and your sample has like a fixed disorder. So then as a result what you have is like your chemical potential can be below some critical energy level or above critical energy level. So or let me just remind you, or E Fermi less than some E mobility h, or so this is the localized case, E Fermi above some mobility h, and this is the delocalized case. So I want to consider this transition, and for that I want to make it simple. Let's consider the Drude formula, and Drude formula is Einstein formula but written in a different way. This is going to be E squared and tau m. I think we derived this, but if you forget how to derive, this is just Newton's equation in the presence of a Dirac. And I want to calculate the n, so let's calculate n. N is going to be, I'm going to consider three-dimensional problem. As an exercise, you can do it in 2D and 1D. So I have to have like some spin d cube k over 2 pi cube. And this is going to be just 2 times 1 over 2 pi cube. And this is the volume of a sphere for third pi k Fermi cube. I think everybody knows this, right? Okay, trivial stuff. And this one is going to give you k Fermi cube divided by 3 pi squared. And I want to write this in terms of mean free path, like introduce mean free path. L is defined as V Fermi times this scattering time or mean free time, tau. Then let's rewrite sigma. Sigma is equal to E squared. For n, I'm going to write this k Fermi cube divided by 3 pi squared. There is like 1 over m, this 1 over m. For tau, I am going to write L over V Fermi. And let me rewrite this. I want to write this like this is m times v is P Fermi, and P Fermi is h bar k Fermi. And I like h bar here because it kind of looks like Landauer formula. Erase this. Erase this k Fermi, and this is going to be k Fermi squared. And this is exactly what I want. Let me write this here, L. And here's something else. Joffe Regel criterion. So what these guys say is like if mean free path is order of your wavelength, right? So you have like some wave going around, but if the wave cannot even complete a full wavelength, right? This wave cannot go anywhere, right? I mean, for a wave, for us to be able to talk about a wave propagating in space, it has to do at least a couple of like Feynman wavelengths from impurity to impurity. Otherwise, it means it's just stuck. So then, okay, this is equal to 2 pi over k Fermi. If this condition is satisfied, no Bloch wave. And if there is no blow wave, no conduction. Then this minimum possible conductance I can have from here is sigma minimum. So I write this, and L can be minimum 2 pi over K Fermi. I just substitute L is equal to this minimum possibility. And it is going to be equal to, okay, let me skip the factors. This is order of E squared over H. There is only one thing left here is K Fermi. And K Fermi in materials are typically 1 over A lattice spacing, right? If lattice spacing is A, K Fermi is order of 1 over A. Then minimum possible conductance is sigma minimum E squared over H. Okay, this is not exact. There's like some overall coefficients times 1 over A. So this is like an important. This is sometimes called Mott's minimum conductivity. And the Mott gave this argument first, and these guys also had some additions. And the argument is if sigma is sigma minimum, then there is no conduction. That's the argument. But of course, this is like a hand-waving argument. Today we know some materials smaller with sigma smaller than sigma minimum, and but that's not the point. The point is like this is giving us a handle to probe to go from like a localized to delocalized state. Any questions? Let's take like a 5-minute break, and in the second hour I will play with Ender's model a little bit.